So in this video, I'll actually do the proof to show that from definition, right, of the cross product. So if somebody tells you the cross product is equal to the determinant of I, J, and K, AX, AY, and AZ, BX, BY, and BZ. From this definition, we can actually prove that the cross product is also equal to the magnitude of A, the magnitude of B, times sine of the angle between them times the unit vector U. So that's perpendicular to both A and B. So we're going to go through this. The proof is it's kind of long, but because there's several steps. We're going to first prove that that the magnitude AB sine theta, the magnitude of this, right, is AB sine theta. So let's start from there. So let me erase everything that's not pertinent because I'll be using a lot of space on the board. Okay, so let's calculate A cross B. So from definition, we know A cross B is equal to A cross B is equal to determinant of I, J, K, AX, AY, AZ, BX, BY, BZ. So expanding in terms of I, that's equal to the determinant of this row and columns removed. So this is AY, AZ, BY, BZ, plus J vector, which is minus, actually there's a minus in sign. So J, determinant of AX, AZ, BX, BZ, and plus K, which is now the determinant of AX, AY, BX, BY. So we can expand this into I vector, which is AY, BZ minus AZ, BY, plus J vector. I'll put a plus now. I'll do in reverse order. So this is AZ, BX minus AX, BZ, plus a K vector, AX, BY, minus AY, BX. Now the first step is I'm going to take the magnitude of this squared. So we're going to write this as the magnitude of A which is this squared plus this squared plus this squared. So hopefully there's enough space to deal with this. AY BZ minus, AZ BY squared plus AZ BX minus AX BZ squared. And then we have AX BY minus AY BX squared. So we have this long expansion of A cross B squared. Now we can expand these terms out, so we'll get three elements here. So something squared plus something squared minus 2 this times this, and we can repeat this for both sides. And so we'll get 3 elements here, 3 elements here, and 3 elements here. And if you kind of look at it carefully, let's see if I can Okay, so we'll get ay squared bz squared, and I don't want to go through the steps of actually expanding, because I'll try to do this mostly in my head, because it's time consuming to expand it, especially since I don't have a lot of space on the board to do this. So what I'm going to say is that what this looks like, right, is so there's square elements here, minus 2ayzbz by. So there's elements there. So what I'm going to do is say that these elements, right, can be constructed ay squared bz squared and az squared by squared elements, az squared bx squared and ax squared bz squared. Those elements can be constructed by taking the product of ax, so we want squares everything, so ax plus ay squared plus az squared multiplied by bx squared plus by squared plus bz squared. But I'm going to have to subtract by elements, so there's some elements to get the square elements from the top row. I have to subtract by the elements that are the diagonals, which are like so when I take these two products, I'll get 9 elements. There'll be 3 extra elements consisting of terms of ax squared, bx squared, minus ay squared, by squared, minus az squared and bz squared. So this basically are all the square elements, but there are the inner elements of like the this times this minus 2, so I'm going to have to put those in. So this is equal to this, 9 elements, minus 2 ayaz bz minus the middle element from here. So this will be 2 ax az bx bz, okay, minus 2 ax sorry, so this is ay bx by. So anyway, so if you think about it, right, you'll actually see that those elements must be the same. Now there's better ways of evaluating this, but the math is a little more advanced, and so I'm going back to basic algebra to do these problems, to explain these details, the proof of this. So this is good, and then we have these ax bx squared minus ay squared az squared, and let's see. So it's a little tricky. Ax, ay, z. Ax squared, bx squared, ay squared, by squared, az squared, minus 2ay. Okay, actually, so what I get is ax squared plus ay squared plus az squared times bx squared plus by squared plus bz squared. And then there's a, okay, so to get, so okay, so if you look carefully, right, this looks like nothing more than ax bx plus ay by plus az bz squared. So take a look when you, so remember there's 1, 2, 3, so you break these apart in 2 pieces, so there's 9 elements here. So each of them corresponds to ax bx squared, there's an ay by squared, and there's an az bz squared, and then there is a ax, bx, ay, by, which is here. And then there's a term that's ay, by, ax, which is twice, two terms. So this is your rule. And then there's an ay, by, az, bz term here. There's two of those. And there's two of these ax, bx's. ax, az, bx, bz. So this corresponds to this. So anyway, so I kind of did a couple of these steps in my head, or so hopefully you can actually see it. I just didn't go through the expansion of everything because it's time consuming to do this. So, and also I have a general idea what the solution is going to be anyway. So anyway, so this is basically, what is this? This is nothing more than a squared. This is b squared. And this is actually a dot b. So remember, this is the definition of the dot product of two vectors squared. So this is actually squared. And so, but I know that this is really a squared b squared minus ab. Definition of dot product is the angle between them. So this is squared. And you can actually see that we're getting the answer. So we can pull out a squared, b squared, 1 minus cosine squared theta, which is a squared, b squared, sine squared theta. And so we're left with that the magnitude of a cross b is equal to the magnitude of a, b, which is a positive anyway, times sine of theta. So maybe I'll just put the magnitudes in. So a cross b, so all I know is that the magnitude of a cross b is equal to ab sine theta. So remember, I'm trying to prove that a cross b is equal to ab sine of theta times a unit vector. And so the magnitude of this would be ab sine theta. So this is a magnitude ab sine theta. So, okay, so we've done the proof there. Next I have to show that this u vector, right, is perpendicular to both a cross b. So let me go back to this original definition. And so all I need to now show, right, is that I have to show that there's a unit vector, and that's vector is perpendicular to this. Or more simply put, I have to show that a cross b is perpendicular to a. And it's actually this idea. So I have to show that a dot a cross b vector is equal to 0. In that case, and I have to show that b vector dot a cross b is equal to 0. So if you look at it, we have, so basically, so just a little side note. Now, whenever I do a dot b vector, right, that is axi plus ayj plus azk dotted with bxi plus byj plus bzk. So we know that's equal to ax, bx, so it's an idea because we're going to use it in the triple product also. So hold on a sec. It's a very subtle idea, so let's make sure you get the subtlety out of this. So I've got a vector axi, ayj, azk, and I dot it with bx, and I get this. One way of constructing this way of like writing this answer is everywhere that I see the I vector, right, I replace with bx. So it's actually a rule. We've constructed a rule. So here's the dot product is equal to this. So my construction of the rule says that if I have a vector axi, ayj plus azk and dotted with bxi, byj, I will transform this rule into saying every place where I see the I will replace with bx. Everywhere I see the j in the first vector, I'll replace with the second vector. Every place I see the bz vector, right, I'll replace with, the k vector, I'll replace with bz. So that's a rule. Let's see if we can apply this rule in evaluating this. So let me erase this. So it's a subtle rule. So instead of saying, I'm saying the same thing, it's just instead of actually saying that this is really ax, bx, ay, I'm constructing a rule that says if I have a product of two vectors, every place I see the I, I'll go to the second vector and replace the b and place it there. Every place I see the j vector, I'll place it with the second component. Every place I see a z or the k vector, right, I'll replace with the third component. You get the same answer, but I'm actually have a rule for construction. So let's go back to the construction. So a dot a cross b, so these are vectors. So from definition, we know the dot product, right, doesn't matter the order, so I can replace this with A cross B dot with A. From definition, right, I know that this is the determinant I, J, K of AX, AY, and AZ, BX, BY, and BZ. I'm going to dot it with AXI plus AYJ plus AZK. So we'll go back to our rule. Every rule says that every place I see the I, I'll replace it with the first component of bx. And so what you're saying is the answer must be replace the I with the first component. So that means that's a determinant from definition, from our understanding of this rule construction. And J, I'm going to replace it with AY. And every place I see the K, I'll replace with AZ. And so I've changed the problem so it looks strange, right? But I've constructed a determinant directly from our understanding of a dot product is really AXI plus AYJ plus AZK, BXI plus BYJ plus BZK. And the replacement to get to here is every place I see the I, I'll replace it with the first component, the second vector. First, so J is going to be replaced by the second component, second vector, and so on. So I've constructed a rule, and I've applied that rule to solve this problem. So in this case, this is this. Now, we can actually calculate this, and you might say, well, I don't know what this is, but if I select, for example, if you know determinants, two rows automatically, right, in a determinant means that the determinant is 0. But if you didn't know that, right, let's expand in terms of this row, in which case you'll get a plus bx times the determinant of ay, az, ay, az, and this times this is 0, so this whole term is 0. There's a minus by times the determinant of, same thing, you'll get ax, az, az, and product, cross product, again, this is 0, and then bz is equal to, we take ax, ay. Hope I can see this on the board. Yeah, I think you can. Yeah, barely. And this is ax, ay. Again, the cross products are 0, so this whole thing is 0. So what we've just shown, right, is that a vector dotted with a cross b is equal to 0. It means that this vector, right, is perpendicular to a cross b. So we know that. We can repeat this process also for b. This type of construction, right, where I have constructed an algorithm that basically said that every time I see I, I'll replace second, we can actually use it to define something called the triple product, which will be another next video. I'll be discussing triple product. But actually, I have to do some examples of more, so I'll delay that a little bit. But 2 videos from now, hopefully, we'll get this. So we can repeat this process for B. So remember, what we're trying to say is that a vector dot a cross b is equal to 0. Means that the dot product of two vectors that are not zero means that this vector is perpendicular to this vector. So A cross B is perpendicular to B. We can repeat this process again with A cross B, and I can rearrange this in terms of saying it's really A cross dot B vector, and then using that idea of transcribing the i's and j's. So this is your cross product. I'll get that the determinant of bx, by, and bz is equal to ax, ay, and az, bx, by, and bz. So the determinant, if I expand in this, you get the same answer of like getting a determinant, which is 0. So if you go through the steps of expanding, and the minor matrices will be, the first one will be by, bz, by, bz again. If you do the difference, you'll find that 0. So anyway, the determinant is 0. So A cross B is perpendicular to A, and A cross B is perpendicular to B vector. We also know that the magnitude of A cross B is equal to AB sine of theta magnitude. And so we can actually put these together and then say that the cross product of B is nothing more than the magnitude of AB sine theta. Okay, AB sine theta, assuming theta is actually between minus pi over 2 and pi over 2, 90 degrees, so it's positive all the time. AB sine theta times the magnitude vector u, and that u vector is perpendicular. So we've actually shown that whatever that vector is, it's equal to AB sine theta. So basically, starting from this definition, we can now show that that's equal to AB sine of theta times a unit vector that's perpendicular to both sides. Okay, hopefully you didn't totally get lost in this, but anyway, this is the proof, but I kind of didn't write down, I guess I could be cleaner, but I would require a lot more space than this, and I just have I'm limited by the amount of stuff I can write on the board. Anyway, it's not important that you actually know the derivation of this and the process of this, but you do have to memorize this. So it is required for you to make sure you understand how to do A cross B, and is the determinant of this matrix, and then it's the magnitude of AB, sine of the angle between them, and u. And anyway.